So thank you all for coming. I feel I'm a celebrity, but actually you didn't come for me, maybe for the cookies itself, but yeah, thank you so much. So the idea behind this workshop is like give introduction to machine learning and taking off all the massive stuff so you can like easy going. So it's two parts. The first part is like getting the intuition and the mechanics behind the machine learning. The second part is about the coding, how to build like ML application. We are going to use Google Colab.
I'm bringing a lot of free food.
Yeah,
I think we have too much.
I came for the food. So the thing is like, it should be like in 2 weeks, but because of the spring break, we may like delay it a little bit. So this is my name, Mahmoud, and it's presented by the iCORE, and the director is Dr. Scott King. I have to say this. I'm celebrity. You don't know. So the outline is that we're gonna, through the introduction, kind of the motivation why we need machine learning, and we're gonna through the mechanics through an example. There is a lot of like popular algorithm in machine learning that's usually used before, but we're gonna just take a glimpse on them, and we're gonna focus on the most common ones like the neural networks and specifically the convolutional neural networks. And we'll end up with summary. What? It's a hey. So what is actually machine learning? It's a technique or a methodology or whatever you say to find like important information in your data, like building a program, but you don't have to write the program yourself, like web development. Any experience with programming before? The cool thing about machine learning, you don't really need to learn about programming. You let the machine learns, and you get a kind of a program out of it. But you have to give it some data, and it learns the program like from the data implicitly. It's very different from traditional programming, like web development. We have to specifically write the code to do some stuff. And the main like theme for traditional programming is like you have your input, you write a program, and you get some results. But on the other hand, for machine learning, you have the input, you have your results, and you kind of get the program or the model for the thing. To make it a little bit clear, this is kind of the traditional programming. You actually write the program, it's kind of the blender, and you have this oranges, and you get your orange juice. But in the machine learning, it's actually you give it the orange juice, and you get the program. The thing about the program is not a fancy program. It just does the thing you want, more or less. Sometimes it breaks, but yeah, it's a machine learning. It learns. So there is a landscape. The landscape for machine learning is actually quite big. Like there is 3 main tasks: supervised, unsupervised learning, and reinforcement learning. It depends on the data you have, like what task you want to do. It depends on the data. As long as you have the input and the output, or the inputs and the answers, you can go for supervised. If you don't have the answers, you can do some unsupervised stuff. It's gonna be clear. And the reinforcement learning is like if you have some answers, not the whole answers, but if you have some. For this presentation, we're going specifically for supervised, specifically the classification. And we're gonna learn a little bit about this. So, okay, this is the machine learning, but actually why we need machine learning? Any idea? If we can write programs, why we need, sorry?
Take time.
This is part of it, yeah. Yeah, another one.
Predictions based on
Yeah. Sometimes all of these are important. Like I'm kind of lazy to write a program, so give the data to the machine learning algorithm, I get the program. Large data for sure, yeah. It's difficult for a human to analyze the data. But the main thing behind machine learning or the motivation, we actually can't write the programs. Like if I want to like detect the people here in the room from an image, I have to write a program. And changing the lights, maybe people come and goes. Actually, the program kind of breaks. So we need somehow like to generalize our programs. Like this is specifically for tasks that we can't write the programs for. But yeah, for sure, there is a lot of things. So to go through the mechanics of the machine learning, we're gonna try to answer one question. And I thought a lot about this question, and because like 2 weeks ago it was the Valentine's Day. So here's the question. Is the gift you got was expensive or not? You don't have to answer it. I'm not trying to devalue your present, okay? But still, like, if you know the price, you can tell if it's expensive or not. So if I want to write a program for this, it should be simple, like straight. If it's past the threshold, certain amount, it should be expensive, like more than $100. Otherwise, it's gonna be like not expensive. But let's see. So this is a simple program. But the thing is, like, what is the amount? Can you figure it out? And actually, this amount is gonna differ from me, you, other people, right? So this is, we can write a program. Actually, we wrote a program. But we want to see how the machine learning or the algorithm gonna like reason for this program. So let's try it out. By the way, the machine learning needs some data to reason. So we don't have the data yet. So let's try it. So I'm gonna ask the question for myself. So what is the price for the gift to be expensive? This is my opinion. So can you guess? And keep your guess to yourself. I'm not a very cheap person, but maybe I'm a cheap person. But
I think it's relative to what you, like your budget, like how much money you
Yeah.
have. I think it's relative to that.
so I'm a student, so take a guess. Not much.
For you, graduate student, Valentine's Day gift.
Any guess? Yeah, I'm cheap. So did you?
It's for your advisor and there's nothing that's too.
Yeah.
For Amanda or give it to somebody else?
So did you pick a number? Nice. I like the number, but you should. The thing is, like, because you don't have any information, you pick a number, like you make a guess. But if I give you like 100 is expensive, did you change your guess, or your program is perfect? By the way, we have the program. All we need to answer is like how much. Did you change your number? You probably changed your number.
Every program. Josh.
Perfect, yeah. You should see. Okay, so if I give you 120, did you change your number? So the 100 should be enough to like instead of the 120. There is, so you should be fine if you adjust your number below 100, right? Okay, but if I give you 20, it's not expensive. So did you change your number? Yeah, you're writing the program. So these are the last two numbers. Nice. So I had a lot of information here about like 5 samples. It's based on my opinion and only opinion. But actually, there is a lot of redundant information. Like the only thing you need is like 20 and 50. So the number should be between 20 and 50. So again, this is your final chance. The closest one gonna get like $10 from the true number. So 75. This is close, yeah. So pick a number because end of the presentation, I'm gonna show the number for sure. I picked it before and I wrote it on the presentation, so I don't change it. So 69. It's actually close to, but I'm gonna tell the number at the end. So
68.
keep guessing.
67.
Pick a number and you'll find the thing is, like, we wrote actual program, and you actually pick a number, and based on the data, it's a correct program. But this program only works for me, so it doesn't work for you or any other one, except you have the same number as me. So let's try a little bit. So if we ask another one and he give this amount, it's not expensive if he did like $1K, $1,000. So does it still your amount is correct? So what is the correct amount now? It depends on the data. How you pick a number now? Tell me. Yeah, this is one way, but it's not a trick question. Like I added something here, but actually you can't solve it. Whatever the number you're gonna pick, there will be someone is incorrect. Like some example is incorrect, and in this way you kind of like pick the number that maximizes the correct answers. Maybe it's the 67 or the 68. It's gonna be still correct. So the thing is, like, actually to solve, I'm not trying to like really. It's not a trick question, but the thing is, like, if we add the income, does it help to solve the thing? But in this case, you're gonna need to use the price and the income to actually know, like, you need the two pieces of information, the 180K and the price of the price. So is this like clear? Questions so far? So the thing here, the machine learning is trying to search in the data for certain patterns. And this is tabular data. It's just an Excel sheet where we have some input information. Whatever the information you can give, you can put like 1,000 information, 1,000 of columns, and you try to estimate something, an answer. And it's just to try out, take a guess based on the information and try to measure and start refining its guess. So for this case, we're only using the income and price, but this is kind of like irrelevant now. So you probably picked up how machine learning works, I think. So all the machine learning algorithms that we saw in the beginning, more or less use similar strategies, like pick a number or pick a guess, pick a pattern, and try to refine it through the data. And by end of the learning process, this is your patterns and try to associate it with certain answers. Like that. In our case, it's using the income and price. Probably next time, gonna like try to code this thing. It's not like 4 or 5, 6 line of code. So the rest, it's a pretty straightforward to some extent. So this is the mechanics of the machine learning. It starts by initialization process. It's have initial guess based on the price or the income or the feature you give. And hey, I picked a guess. It's a numerical thing. And start iterating, like try to refine these numbers a little bit higher, a little bit lower to get like certain accuracy. And by end of the program, this is your thing. So what you're gonna get is like templates of like income and price and associate the expensiveness with these patterns, like list. So just to give you like a little bit of like in real life situation, if you try to park your car, you may need some help of some guy, like try to park your car. This is kind of adjusting your position. The same with the learning process. But the thing, if you trust this guy too much, you may end up like this. And by the way, you already parked the car and it's correct, but this is not the correct position you want to be in. So any questions so far? Yeah, you don't need to trust Tesla that much. The thing is, like, more or less the machine learning algorithms do the same thing. The popular ones like decision trees or random forest support vector machine and gradient descent, it refine the assumption. And these kind of like, I don't like to use the term classic algorithms because all of these algorithms somehow classic. but it's used before the era of deep learning, and it was very popular, really popular, and it was very simple stuff. But again, it works by the same mechanics. But here comes the neural networks, the most popular machine learning algorithm, or the deep learning era. And it's pretty much the king of all machine learning algorithms. And all the difference between machine neural networks and the previous models, we actually can make it like more complex, looking for more patterns. This is the structure of a shallow neural network, where we have like the input information, your table, the income, the age, the price, and we have like some like nodes here. These nodes like computational node, and the last one is like give you the answer: is it expensive or not? So let's try to see like because we're trying to avoid math. So let's call this node Bob, and it receives the information of these things. How it's gonna reason about this thing? You have the income like 800K, your price gift is 1K. And for example, you give it your age, 25. How do you think, based on the table you had, like how Bob gonna reason about this? It's the thing is here is like try to give some importance value for the 3 different things. So how do you think it's gonna reason for it? At the beginning, how do you think it's gonna work?
It checks its data against the test data in the set.
Yeah,
Looks for a pattern.
it looks for a pattern. But how is this? It's gonna like give it like the initial view is gonna like, for example, like all the pieces of information are important. So it's gonna give like equal weights for all of these. Like the age is important, the income is important, the price is important. But based on the data, you're gonna find the importance like deviate only to the price and income. So the way Bob like tried to say like these features are important or not is like by adding some values that Bob selects and adds a little bit of bias, because Bob has a bias based on, and not only Bob does this, Bob, Alice, Frank, all the rest of these nodes try to receive the data in a way from during the learning process, and the end node start like collecting the data from Bob, Alice, and Frank, and decides like if this is gonna work or not, like get like good results or not. So if we try like this, you can actually see. I put some colors. Like here's the orange, the yellow, and the other orange, and give you like some black thing. But if I change the colors a little bit, it's trying to classify black or white. So if I change the colors, you get something different. And hopefully you can see some patterns. And the neural networks, in a way, like you have like a group of people try to like assess the input data, and if they see it important, they're gonna like flash some signal to the next person in line, and the next person start like accumulating these signals and decide if this is important or not. Any questions so far? Okay, so by changing the input data, the signal varies and the decision varies too. So the trick here was like the orange colors are going to black, the yellows, the dominant yellows are going to white. The thing is, what if the colors are not really orange or yellow? There should be some tolerance, because the data you give during the training doesn't have to be the same as the data you test the program with it. So it's kind of added a little bit of tolerance. So this how the thing works. Questions for so far? Anything? If it's shallow for you, like
what are the different colors representative of?
the orange and the yellow is like high and low. The red is representation of the orange in another layer. The dark yellow or the brownish is a representation of the orange.
Okay.
The black and white is like true or false thing. So the thing about the neural networks is actually the thing about makes neural networks distinctive about the other machine learning algorithms. Actually, you can stack these layers a lot, and you can create like really complex functions. But this is more or less the basics of machine learning. So the thing here, we have the neural networks, and it works for like tabular data, Excel sheet. We have the input features and the output. But what if we have images? How can we deal with it? Okay, but this is like instead of like vector, it become like a raster or like a matrix. Matrix. Yeah, kind of. The thing is like the neural networks expect like input vector, like a list of variables or list of thing. What we can do, we have this image, we can flatten it out, like make it like side by side. But this is not the most efficient way to capture the data. There is another specialized version of neural networks. Have you heard about the convolutional neural networks before? It's pretty much. This should be easy, at least for.
I don't want to give all the switching away. I'm trying to follow the narrative right now.
Yeah, the thing is, we use convolutional neural networks. And instead of like having the vector, we can have like a square of information, and it's a pretty efficient to be the best, to say the least. The thing is like what happens inside the neural networks or the convolutional neural networks. Any? Yeah, it's really mad. So before going to the depth of, it's not really depth. Before going to talk about convolutional neural networks, like we need to learn about a little bit thing about image processing things. It's called kernels or filters. These things like it's like your Snapchat when you apply a filter in your face, but this is more basic. So we have like bunch of numbers. You can like kind of like apply it to the image, and you can get some part of the image. This one is like looking for the edges, the changes in color. Another one is like sharpening the image. One is blurring the image. And these actually 9 numbers. The image can be much bigger than this, 100 by 100. And the way they work is like this. It's like you have this your kernel and try to slide it over the image. And whatever it actually multiply the numbers and sum together and put here in this pixel. So this is the traditional way of doing like image processing for computer vision before convolutional neural networks. And it was working great. And people use this for face detection and even car detection, pedestrian. But you have to actually design these filters. And guess what? We didn't do much of a good job for everything. So, sorry?
It's on the first map, it's on the left, and not very much to touch.
It's not educated. I got it from Wikipedia. So. The cool thing is like, I have a website where you can have like, it's here.
This website.
You can actually like make a filter and apply it in one image. And actually, I found this filter for the sharpening and the image detection. The thing is, it's actually like try to measure the variance between the center pixel and the neighboring pixels. We can add more negative ones here to make it a little bit sharper. You put the 5, if it's the same pixel, like the neighbor with the same value, it's gonna be 0. So you kind of like filter out this here to get the colors. But yeah, it's not that important. Actually, the thing is about the filter, you can make it smaller or bigger. It's just a square of numbers. The thing is that the thing about like kernels or filters, it's actually a very powerful tool. And it's basically was used before the convolutional neural networks. And yeah, it did a decent job. But usually it works a little bit for the low level features. But if you want to like detect a face, tree, a vehicle, buildings, actually you need to spend a little bit of time to design your filters. And again, it usually works for a certain data set. It doesn't like generalize to other things. So instead of like designing the filters ourselves, we're gonna let the convolutional neural networks do it for us. And one of the things here, actually, this is more or less the same thing for the shallow neural networks, but instead of like looking for vector data, we're looking for matrix data. The thing here, if we have this image, it's 28 by 28. The thing is like we can apply some filters similar to the machine learning, similar to the image processing. Here is the filter. The cool thing, when you apply the filter, you can get something out version of these images. So it's 32 images of this one. We try to select multiple version of the image, and each image of these represents a specific feature based on the kernel or based on the filter. The cool thing about this, you don't have to apply a filter for one time. You can like apply another set of filters over these. So this is how convolutional neural network works. You can take the output of this phase and apply another kind of filter and keep applying filters to get the whole thing. The cool thing about these filters, you don't have to design them yourself. The machine learn them. How they learn them? They actually initialize this filter randomly. Actually, it's not randomly. They have like certain distributions to kind of maximize the learning or the benefit. And during the learning process, these filters kind of learns what's in the image and actually can detect faces, cars, buildings. Questions so far? It seems trivial, but the thing is like, yeah.
So on each, are there like multiple different kernels being developed for the different layers of the nodes of the hidden layer or something?
Yeah,
So like each kernel detects like a specific feature.
specific features.
just detects.
Yeah. The cool thing here, like you can set the size of the kernel. Usually it's 3 by 3. This is the size of the kernels. And in another layer, like future layer is still also 3 by 3. But the cool thing is like the first filter only sees 3 by 3 of the image, like only 9 pixels. But because we're applying the filters and kind of summarize the 3 by 3, so this kernel is not looking for 3 by 3 or 9 pixel in the image. Actually, it's looking for 49, 7 by 7 in the original image. So as you move forward, your receptive field of the kernel actually increases, even if the kernel size doesn't increase, because it relies on the pre-processed information. Does it make sense? You're gonna see it in a bit. But by end of this, these filters is like pretty focused in the early stages, looking for small details. And as you move forward with the layers, you start building a bigger picture, your input.
It's almost as if your abstraction, each iteration is an abstraction of the big picture given.
Exactly, yeah. The cool thing, again, you don't have to design these filters yourself. It's actually because you have the data, you give it, here is my data, here is my output or my expected output. It's gonna learn these filters by itself. This is actually how these filters work. and this filter is actually extracted from the network. Actually, you can like view the network, like you can extract the information out of the network. Questions so far? It's pretty fast, but this is how the filters are being applied. Does it make sense? We're gonna see it. Okay, so it's actually like CNNs is the state of the art for vision tests. I'm actually using it quite a lot. And basically, it's a sequence of filters where the output of each layer is going to a set of filters in the next layer. And this is how you get like bigger perceptive field. Kind of hierarchy of patterns. I'm not in the picture. Okay. You just put my name on it. But anyhow, so it's a hierarchy of patterns. Like, thank you. Yeah, I wish I wanted to be a stand-up comedian, but it didn't work. So it's a way of building these kernels. The thing is, like when you design a kernel, you only think about only one kernel, maybe two at the time. But this way is like it's building a whole hierarchy, and it's you're building bigger receptive fields along the network, so you actually cover the whole image. The other thing go ahead. Yeah, you can do this, and in 2 slides, we're gonna see like what the internal kernel sees, like what they look for. It's like a scanning the image, sliding window. So convolution is like more specialized neuron, only looking for square things, and it learns all of these from the images. Yeah. So there is so many things like you have to design when you do a kernel, like the size, the weights, or the parameters you have, the semantic value, what is it looking for, and many of these are design filters for face detection. And there is the ancient cameras like had like face detector. It was actually ancient technology. They designed the filters and actually patented. But the thing is, like, this is one of the first convolutional neural networks, the Net5. It's developed by Yann LaFoon. He's a big name. But his neural network is like trying to convert like handwritten digits to classify them like actually like get the value of the numeric value to automatically like classify if you wrote a check and you have like the amount, it classifies how much. And the output of the internal layers. He had like 3 layers of introductions, and actually it should be 5, but he only displayed these 3. And the cool thing about even more, these actually trained on like images, and these are kind of the kernels inside the networks. So what they respond. And this was in layer 2. You can see parts of the face, but the next layer started seeing a little bit more of the face. So along the neural network, you can actually extract what this specific kernel is looking for. And this is actually part of Evan's work for the XAI. It's a little bit different because he doesn't work on faces or human being at all. The thing is, like, these actually some of the classes they train the network for, and you can see again, like the earlier the layer, you can see only parts of the thing you're looking for, but as you move forward, the receptive field is increased and start like making sense of like it groups like these parts together, and as you can like if you move forward, you can maybe see a whole human being. So questions so far? It's a pretty theory. It's pretty anyhow. So the cool thing about these, you don't need to know much of programming. More or less, you copy the code and change your data with the data in the code with your own data. Adjust a little bit of things, and you get like a model for your specific task. But the thing is, like we use like Python is the main programming language for all of this. It has a lot of tools. Like the main deep learning libraries is TensorFlow, PyTorch, and Theano used to be one of the main ones. Scikit-learn, an old one, but mainly TensorFlow and PyTorch. All of these are helpers to load your data, feed it to the network, and train. The cool thing about Python, you don't need to really know anything about programming. It's very expressive, and you just type your code. Again, we don't use any IDE. We use like some sort of IDE called notebooks. It's interactive. We can put your code and actually don't need it to install anything at this point. But the thing about Python and notebooks, Google thankfully put like set of servers to host like the Python libraries, the TensorFlow and stuff. And you can actually, just by using your Gmail account, you can connect the Colab and write your own code without doing anything. And I think you get it for 12 hours to run your code. Most of the main libraries are installed. You only need to like load your thing.
You get it as long as you want. It's just
You have to be
sign back in every 12 hours. Right? So you can't leave it just running and go away.
Or you can start paying money.
Well, yeah, so pay money though, you get to 24.
The thing
Or
is
you pay
like
a whole lot. And you-
the thing is like you need to save your state to some extent. Paid or not paid, like you have to. So hopefully next time we're gonna start doing the code. Usually we're gonna use like TensorFlow or more specifically Keras with Python and a little bit of Scikit-learn. Scikit-learn is amazing, but it doesn't cover the most advanced convolutional kind of thing. Like it doesn't take advantage as much from the GPUs. But yeah, anyhow. So Google Colab is a good environment for building codes, and you can run your experiments as long as it doesn't take that long. So this is pretty much it. So to summarize the things about machine learning, it's meant to be short, by the way. So to summarize, the machine learning is actually it's a way like when you have trouble or to write a program, or actually you can't write a program, you can do it. And based on the data, you can choose which flavor you want to use. Because sometimes, like, for example, like ChatGPT, it generates text, but they actually collected text from internet. So it's not kind of supervised version, it's kind of generative. What they do is like creates gaps in the data and start like try to make the machine learning try to predict the missing words or the missing sentence, and it works pretty fine. So it's an unsupervised way to make something, but for the common part, you usually have your data, you have your image, and you want to like figure out if it's has a cat or a dog in the image or not. And if you depends on your data, you choose your flavor. Most of us like use supervised learning. The thing is like you need to understand it's not like science fiction or magic inside the neural networks. It's a guessing game. And once you design your network, like how many layers, how many neurons in your network, it's actually try to fill these capacities from the data. Exactly. And if it doesn't get the results you want, you need to know how to debug this. And this is the way you kind of debug it. So the magic the true magic of the machine learning is actually the gradient descent, how you adjust these kernels, but you don't really need to know how it works. It's just like if it's too high, it's gonna lower it down. If it's too low, it's gonna increase it up. But this is actually pretty cool. But yeah. So again, hopefully you can use the neural networks in your work. And yeah, for the next time, we should like do the collab and start coding. I can start coding now, but anyhow, the thing is, the thing I want to ask you, the closest one to the number I made you, he's gonna get or she's gonna get $10. So I'm gonna take your word for it, but the number I picked, it was like, it was a hard number, but yeah, I should say questions, but it was 79,325,7,523. It's not a phone number, it's just a number.
So we
You said 75.
split the five.
Yeah, I have to actually. By the way, any questions? You said 69.
You have questions in the chat.
I have a question. So
Yeah, check the chat.
I'm trying.
Evan put 79. He looked at the slide.
Yeah, the guy 4 decimal places.
He saw the slides. So how many of you know how to install Python?
Hey, Larissa.
How many
So
don't know how to install Python?
what is the difference between?
So use Colab, you don't have to install it. You don't have to install anything. All you have to do is have a Gmail account and everything else is done. So it's a really powerful tool, you know, as long as you already have some. If you don't, Gmail is easy to get, but if you're one of those people who don't want to get a Gmail account, then you can't use it. But if you already have one, all you have to do is just log in.
So Larissa saying is like, what is the difference between Keras and
Install them how?
TensorFlow?
Install them how?
What was that?
Larissa? She's asking what is the difference between TensorFlow, Keras, and other similar libraries. More or less, they do the same job. Keras is a in top of TensorFlow. It's used to like simplify tasks for using the actual gradient descent and all the machine learning stuff. But PyTorch, another library doing the same thing as TensorFlow. The thing about PyTorch, it's developed by Montreal University and it's free and it's already free. TensorFlow is developed by Google. I'm not sure.
He mentioned, how CNNs work, right? You have all these different weights for the filters, right? How do you come up with those? Well, there's an algorithm to do that, right? They implement that, right? They implement the algorithm to actually do the learning. All you have to do is build your model and say train, and you call the function already doing it. So that's what those libraries are for. It's different ways of training your model and building it. So it's just a library that has all the infrastructure to do that. So you don't have to implement it, right? Back when Dr. Tissot started doing this, you had to write your own, and so it was the barrier was much higher to get into it. Now you can create one of these CNN models in a matter of minutes.
So building on that, I mean, yes, like Mahmoud said, Keras is on top of TensorFlow. So it's like TensorFlow is a more I guess you have more options. Keras is simpler.
Just give us a second.
Yeah. Is Evan answering it? What's he?
Yeah, he didn't listen. He's saying something. Can you say your question again?
Okay. So I was just talking about that same answer. So TensorFlow, Keras, and when we say other similar, that usually means PyTorch. Yes, Okay, are you guys muted now? I'm trying to answer something about TensorFlow versus PyTorch. Okay.
Go ahead.
Okay. So
Just pause. Evan, pause for a second because somebody's asking a question. And you might be the person that answered.
Yeah, he stopped.
Okay.
I was wondering how you test, how accurately predicting your data.
Usually you do like validation test split, and based on the test data, you can say like, hey, it's like 90% accurate. Like you split your data into 3 chunks, one for the training, one for validation, and one like you leave it apart for just like you look after you finish training your model. And this you split the data before the training.
There are functions in these toolbox to do some of that for you, but you probably want to do it yourself.
I can elaborate on that. I struggled with that when I was first learning too. Basically, the data is classified. So the section they're talking about at the end, that you know the answer, and then you do the predictions on it, and then you can compare how accurate you were just by using math. So the data already knows what it is. Like if it's a cat, it's got a label saying it's a cat. And if you said it was a dog, then it was wrong. So then you can add up all those rights and wrongs to get the percentage of accuracy.
I think she's asking a little bit different question. So
I remember.
there's a whole lot of theory in the best way to do that, right? Because so typically you want to divide your data into 3 groups, right? So the one is training. So that's a set of data that you train the weights on. And so it's going to come it should get really accurate at that, right? Because it sees that over and over, and it's adjusting the weight to minimize. So what you're doing is you're optimizing the weights to minimize some error, right? And so the error function, there's a lot involved in that too, but so you have some way of minimizing the error. So you're really, really good at that. Well, you have another set you call a validation set. So while you're training the data, you're also evaluating on the evaluation set. So that's an attempt to see, are you actually learning the function, or are you just learning a model that is really good for just this subset? Because you're making the assumption that your training set represents the entire distribution of whatever you're trying to do, which is a bad assumption, right? So the validation, so if it's actually getting better at the validation and it's getting better at the training set, hey, that's good, right? If it's getting better at the the training, but not so good at the validation, then you're overfitting and you got a bad model. Once you do that, you're all done. Then you have this other set of data you call the test data that you test on just before you publish, right? Because you never ever want your model to see that. So this is surprise data it should never have seen. And then if it does well on that, hey, you're pretty confident. Look, it did well on these two, on the testing, or sorry, on the training and the validation. It learned something, and I could transfer this to another set of data so it's generalizable. The challenge is, do you have enough data to do that? How do you pick the data? Because both sets have to be representative of your system, but not be really correlated, right? Because if you split the data and you think they're independent, but they're not really independent, it's already seen the data. So you have to be careful. So it's a lot of theory involved in that, which is statistics. And a lot of people aren't really good at statistics, so they do a bad job on that. Is that good?
Yeah, I like that. It's really about the data. The rigor, instead of being in the math, of the formula, the parameter, the rigor becomes in how you split the data, in how you're managing the data. In the end, you gotta have a piece of data that your AI has never seen. You test it there, hopefully it does well, and then hopefully you designed it such that people are going to be convinced that because your AI does well on this independent data set, then yeah, it's a great generalized model. Or have several sets of data. So, but until now it was enough. You prove it through the data. I think the concept of trustworthy AI now is becoming more and more important. And it's saying that just showing it on the data is probably not enough. But we also need to have explainable AI, interpretable AI, or know a little more about how it works besides having really good results on an independent data system.
Yeah, we're both from wildlife, so it's all very few. But work with spatial data.
Exactly. Yeah. So typically, you know, for like the stuff we do, which is with weather, you have spatial temporal data. So you need to block it. You have to get rid of the autocorrelation both spatially and temporally. Otherwise, it's really seeing the data. So because you really want to get rid of this autocorrelation between data so that it's truly independent. So there's one other little monkey wrench that you throw in there. It's, you know, you said, how do you know what's doing, how you break the data, but how do you know it's doing well, right? You have to come up with a single metric because you're optimizing a single metric. What is that metric, right? Because there's lots of metrics, right? When it's, if you have a balanced case, you could use something like accuracy, but for a lot of interesting is you have an imbalanced case. And so, you know, if you have a minority case and a majority case, if you just always predict the majority case, you might have really high accuracy, but that's a useless system, right? So there's a lots of different things that go into picking that metric that you're going to use. And often we use several metrics.
Choose the one that makes the work publishable.
No,
This is
choose the one that does the answer that helps you actually learn something.
So I always remember the story of their making some model to detect tanks. Found out later on it was detecting the day versus night.
Sure.
Y'all heard that?
Yeah.
So going back to the question of how do you know how accurate you are? How do you know how accurate you are?
Yeah. Well, so and that's so there's you know, so did you do a job? If you didn't do a good job of splitting your data, then that's, you know, and that's typically a bias problem, right? So you bias the data towards nighttime, or sorry, for daytime pictures, and you didn't really test. But as Dr. Tissot mentioned, and also Mahmoud, understanding, I think you asked that question, how do you know what it's using, right? And that's this explainable AI, and that's challenging. If you do, there's lots of cases where it really works well on the data, but it's not actually learning the problem that we've asked it to learn. It's learned something else, like in that case, detect day and night. Or, you know, the example of the wolf is a good example, right? It's detecting snow, not whether or not it's a wolf. If there's snow, because, you know, every time you show it snow, there's also a wolf there. So it's going to use the easiest thing that optimizes that answer. So
the thing, there is some techniques like grad cam. It can point out to the part of the image, like triggering this answer. And there is so many techniques, and actually you can look to the network, like the grad cam.
I mentioned an example, Dr. Medrano shared a link to the John Oliver, which is awesome. And, and he says, well, for melanoma mole, there's a ruler next to the mole is cancerous.
Yeah.
It just turns out to be a correlation that was easy to learn.
And
yeah,
And same thing, there's a classic.
and the other thing, I'm sorry to interrupt,
Go ahead.
but the other thing, you actually can look to what the kernel is looking for, like for the, it depends on like the way you approach the problem, but yeah, you can get the output of the thing like the kernel sees, if it's a tank or a day or night, or the caption in the image, you can get this from the kernel.
and Evan's already done some XAI methods, but he'll probably do another workshop, you know, maybe in fall. So if you know, if you start building your models and you want to learn what is it actually using, then Evan will talk about that.
He said that the shape of the kernel can, if it's realistic, if it's looking at, it's got the right scale or it's the right shape, how you get confidence from the shape of the kernel? And I don't know as much about that.
It's not the shape of the kernel, it's the layers. As you move forward, you usually get bigger perception. But to avoid the thing about the scale, specifically the scale is the most annoying part, is actually to augment the data set to scale and lower the image. The other thing, you need to make sure that you have enough kernels to hold this patterns. So the bigger the better, as they say. but it's gonna be hard to make like kernel like detecting face of like 5 by 5 to make the same kernel like detecting the face at 10 by 10. It has to be. There is a lot of techniques, but the best way is augment and increase the size of the network.
Hey, can I share my screen real quick?
Go ahead.
No.
I only heard Mahmoud's answer, so.
So you hear the other
Kevin always
answer.
hears what he wants to hear.
Yep. Hold on, let me see. Can you
Actually,
guys see?
Not yet. Trying to find. It's Teams.
You may need
The thing is, it's easier for me is to do like this. Go ahead.
So can you guys see it?
Yeah.
Okay. So this was back on just a comment on the question related to like, how do you know you're right? And then people started saying something about spatial data. Keeping in mind online, I hear about every other word. But I just want to throw in this example, right? So let's say we want to create a model that detects this blue line, right? So in both of these images, it's the same blue line. And we've got two models here. The pink line means this is like drawn on by the model. So this is detecting the line. So which one do we like better? This pink line or this pink line over here? So left or right, which do we like?
Can you tell them that we said one answer?
It's the left.
Left, okay.
What are you using?
So that's kind of the thing, right? Visually looking at it, I certainly think the left one better captures what we're actually trying to do with this application. But unless there's a little accident here, I've tried to draw it. I messed up, but I tried to draw it where there's no overlap between the blue and the pink pixels. So if your metric that you're using to capture the accuracy, the performance of your model just says like, how often do the pixels match up? If no pixels match up, then basically the performance here, the accuracy here is 0. Whereas this one, we could roughly say it's 50%, right? So by your metric, this one could look better because half of it matches up, even though clearly this shape is, useless compared to what this one is doing. So that's just a comment on how it's very important to pick the metric for assessing the performance of your model that really captures the problem you're trying to solve. And I will stop sharing.
other questions.
There was one question by Darissa. She said like which like framework you use or you prefer to use, like Keras, TensorFlow, or PyTorch. Usually Keras, one of the easiest APIs or frameworks you can use, but it depends on the example you find. If it's in PyTorch, use PyTorch.
Yeah, and there'll be some new ones coming out. So the rule of thumb for, if you're a computer scientist, so you know how to program a lot. So TensorFlow is much easier to use. It does everything for you. It's very easy to use. The problem is though, when you want to actually start modifying things, it's really challenging. And so, it's the first one you go to, and then it's like, then you give up and go to PyTorch, right? So, if you're a computer scientist, you should be using PyTorch. If you're not a computer scientist, probably TensorFlow is much better for you. Because the other issue is TensorFlow used to be very, very well supported. And it still is, but the developers no longer answer questions. And when they switched over to the latest version, the documentation didn't catch up. And so it frustrates a lot of people. So that's kind of the consensus that I've seen over the last couple of years, is that TensorFlow is much better to use, but TensorFlow is easier to start with. And if you're a non-programmer, you really need to be a good programmer to really notice the difference. or are really doing deep stuff. If all you're doing is just very simple models, TensorFlow.
Another question by Leah talking about JAX. JAX is another framework.
Yeah, there's a couple others. You know, the problem with the
It-
newer ones, they don't necessarily have as much examples out there. You know, and that's usually what happens is you do a web search and you want to use some technique and you follow the tutorial and that's the whatever you use, because that's what was there. You don't end up transferring it to some other platform.
If you have a specialized area application, MATLAB, in my class, I had folks use Google Earth. There's a random forest associated with it. If you're already using you don't need sophisticated AI, you want to use AI for a specific case, and it's part of the environment that you have, I think it's going to get broader and broader.
Yeah.
Google Earth.
Yeah, well, R has,
Yeah.
if you're know R,
Yeah.
R's got some powerful tools. They're not quite as good as mature as maybe the Python ones, but R is a really nice language. It has other tools that you don't have in Python.
The others go on to research new architecture, then iCORE. You're looking at how does AI apply to my area of expertise, like in biological sciences. So you may not need.
So Larissa also asked specifically, is there a preferred one? And my answer for that is yes. The problem is everyone has a different preferred one. Certainly I go with PyTorch.
If Google Earth and TensorFlow are related, I doubt it. I mean, Alphabet's a very big company, and they're all Google Earth's been around for a while, and Google Earth is more on the graphics side, although they have a lot of new stuff in there, but it's mapping and graphics for doing all that stuff, and so it's been around a lot longer than AI. So
I want to show how simple you can write a model. This is the scikit-learn library for doing decision trees. It's super simple to get started with the machine learning.
You need to reshare.
Yeah, my bad. Deep learning is not, even for deep learning, is like you design your model, you have your input data, train and predict. 5 lines of code. And yeah. Can you see it? This is from the scikit-learn. Hopefully next time we're gonna like play with these things. It's similar to the gifted prize thing. And yeah, 5 lines.
So, and for you non-programmers, right, out there. So one of the whole ideas behind iCORE, and I like to call it umbrella corp, right? Not because we zombies here, but because the idea is it's an umbrella for lots of things. The main idea behind iCORE is to bring computer science students to everybody else, right? So you have access. And so we have a lot of undergrads, they have a program, but they don't have a particular problem to work on. So if you have a problem that you need somebody to do something programming and machine learning, right? You can, present it and maybe find somebody here that wants to work on it. So then you can create some sort of, collaboration going. So, there's other ways of getting involved in this than trying to, beat your head against the wall and learning the techniques yourself.
I have a lot of problems.
I get my head against the wall, not because I know how to program. I said, yeah. Other questions. The thing you need to take, it's a simple. Actually, machine learning is super simple, but it's fancy. It works both ways.
It's confusing.
Like that, we use like the gradient descent is actually nice to know, but actually you don't really need to know to make an application. If you want to create a new optimizer, yeah, you really need to. But other than that, is like plug and play. basically.
You know, I think I'd still like to see people using machine learning have a better understanding of just hypothesis testing and understand how to test whether or not their model's actually working. Because too often they do a really bad job of that and they're not proving anything. Right? They just have one time it worked well and they say, hey, it works. It's like, well, you know, a sample of one does not a conclusion make.
It sounds to a certain degree like the lack of knowledge is more on the statistics and understanding the numbers side than making it do what you want.
Oh, yeah.
The conclusion from this is ignorance is a bliss.
Well, I mean, just understanding the exactly what Dr. King's talking about, that you may have a hypothesis and you think you're testing it, but the reality is you've skewed off in this way and you're not getting a result that you're actually looking for. You're getting a result that makes them algorithm happy.
But it's just, the tank. All these examples are where people weren't really thinking, and it's like if I'm making this assumption that I'm giving my test set is representative of my problem domain, right? It's the same distribution, and it's not, right? And if you don't understand that, then you're gonna end up with and that's why we have all these problems, right? Which you'll hear lots and lots and lots of examples of where we've done that, not just in AI, but all throughout technology, where we don't really do a proper job of that. And
But we're not solving the actual problem.
Yeah, we're solving a problem, and we have a solution that works for some cases and some people, but
You can tackle that a little bit by testing variability. Like if you swap data and you test how much does my answer vary depending on what part of the data I'm training for or testing.
Yeah.
Then you retrain several times because a non-trivial portion of the variability is from the recalibration. Because you don't have a global minimum, you have local minima, and that variability coming from the local minima is quite substantial.
Yes.
Environmental science problem. So when you test that, when you quantify the variability, then it will give you more or less confidence.
Yeah, my point is that you can't do it. Is my point. Most people don't know that you need to do that, and they just get one example and it works, and they think I've got a solution.
That's bad.
Yeah.
It's a good start, but it's not.
Yeah.
There's a lot of variation of the deep learning. This is one is GANs, which is similar to ChatGPT, but it generates realistic images, and when kind of refresh, you get a new version. These kind of AIs shows it seems works. It works. I'm sorry. The cool thing about this is you don't need to verify it. It's actually show it. But yeah, you can do a lot of things with deep learning. But yeah, this is pretty much.
Any other questions? All right, well, let's think.
I'm celebrity Evan now. Yeah, thank you so much for coming.